This one is boiler. The flue gas from boiler is passed through chimney. Initially, when the boiler is not fired, this chimney is filled with the cold air. The corresponding column is H. Since cold air is very hot, cold air is heavier as compared to the hot gas. So this column is equals to the density of cold air multiplied by G multiplied by H. When the boiler is fired, the flue gases will pass through this one. Then the density of this one will be lighter as compared to cold air, and the corresponding column will be slightly higher, will be equivalent hot column of air. Natural draught is defined as the difference of pressure due to cold air column minus hot gas column. This is the column due to the cold air, this is the column due to hot gas. The difference in these two is called as natural draught. Because of natural draught, the hot gases will force outward from this height into the atmospheric air. T0 is the absolute zero temperature, is equals to 273 Kelvin. Atmospheric pressure is 1.01325 bar. So rho 0 represents the density of air at absolute temperature 1.293. So T0 is 273 and rho 0 is 1.293 are taken as standard values. Tg is the temperature of hot gas and rho g is the density of hot gas. According to ideal gas equation, PV equals to MRT. M divided by V is called as density, so P is equals to rho into RT. Since the pressure and temperature are constant, since the pressure and the gas constant are always constant, so rho into T is constant value. We'll use this relation to develop the relation between density rho g and rho 0. Therefore, density of air at temperature Tg is equals to rho 0 T0 multiplied by density of air multiplied by Tg. This is density of air at temperature Tg. So density of hot air will be equals to rho 0 multiplied by T0 divided by Tg. Since pressure is given by formula rho gh, so delta P, that is the natural draught, will be equals to rho g into Hg, where rho g is the density of hot gas, Hg is the equivalent column of hot gas, equals to rho w into g into Hw, where rho w is the density of water multiplied by Hw. Hg and rho g are the equivalent column of delta P in terms of gases and in terms of water. M is considered as mass of air fuel ratio or mass of air per kg of fuel. How much amount of air we are firing per kg of fuel is the mass of air upon mass of fuel, is also called as air fuel. The total mass of hot gas form will be mass of air plus mass of fuel divided by kg of fuel is m dot c. So mass of gas per kg of fuel form is always equals to m dot a by m dot c. M dot a by m dot c we are representing by m, and m dot c by m dot c is 1. So mass of gas form per kg of fuel is m plus 1. Chimney is filled with the hot gases. So this chimney is filled with the hot gases, therefore the volume of the hot gases at temperature Tg will be same as the volume of air at temperature Tg. So it is defined as, volume is defined as mass upon density, since mass equals to density multiplied by volume. So mass of air upon density of air at temperature equal to Tg. Mass of air is m, mass of air is m per kg of fuel divided by density of air at Tg, that we have calculated here is density of air at hot is rho 0 T0 by Tg. So m upon rho 0 T0 by Tg. If we shift this Tg in numerator, we will get m into Tg divided by rho 0 upon T. Density of the hot gas is mass of hot gas upon the volume of hot gas, but the volume of hot gas we already find out is m into Tg upon rho 0 T0, and the mass of hot gas, that is equals to m plus 1. So mass of hot gas is m plus 1, volume is equals to m upon Tg, rho 0 T0, so m Tg, this will be shifted in numerator, so rho g will be equals to m plus 1 into rho 0 into T0 upon m into Tg. Let Ta is the atmospheric temperature and rho is the air density at Ta. So rho 0 T0 will be equals to rho A multiplied by Ta, which is the cold temperature. So rho A will be equals to rho 0 T0 upon Ta. When the boiler is fired, this complete height h is filled with the hot gases with density equal to rho g. Therefore, the pressure of hot gases in chimney at the grate level is given by density multiplied by g multiplied by h, where h is the height of chimney. We already find out density is m plus 1 rho 0 T0 upon m Tg. So we'll substitute here for rho g as m upon m plus 1 upon m into rho 0 into T0 rho 0 T0 upon Tg multiplied by Gh. The pressure due to cold air outside the column at a grate level. Outside is cold air and this column is again H with the cold air density is rho A, rho 0 into T0 upon Ta. So pressure is given by a product of density multiplied by G multiplied by H, where rho A is the density of the cold air is rho 0 T0 by Ta multiplied by G and multiplied by H. This difference in the two pressures is called as natural draught. Natural draught is the pressure due to cold air is minus pressure due to hot gases. This pressure is more because density is more because it is a cold air, and the rho g is less because it's a hot gas. So delta P is called as natural draught is P of cold air is rho 0 T0 by Ta multiplied by Gh minus m plus 1 m rho 0 T0 by Tg into Gh. We can take out certain common here. Rho 0 T0 is common, Gh is common. So what is left in this equation is 1 by Ta, and from this equation is m plus 1 upon m into 1 by Tg. Rho 0 and T0 are basically the temperature at absolute zero temperature, and rho 0 density of absolute temperature is 273 and 1.293. So this is the fixed value is 1.293 into 273 is 353. So we'll replace rho 0 T0 by 353. So delta P, that is called as natural draught in Pascal, is 353 multiplied by G multiplied by H 1 by Ta minus m plus 1 upon m into 1 by Tg. The delta P equation that we have developed just now is 353 Gh into 1 by Ta minus m plus 1 upon m into 1 by Tg. We can express this pressure difference in pressure either in column of gas or either in column of water. So let first express with the column of gas. So delta P equal to rho g into G into H, 353 Gh. So here G and H. So this is the rho g into G into Hg. So we want to solve for Hg. So we know the density of hot gas rho g is m plus 1 rho 0 T0 upon m plus m into Tg. We will substitute this m plus 1 into m rho 0 T0 into upon Tg multiplied by G multiplied by Hg equal to 353. Here G and G can be get cancelled, and this product, this is rho 0 and T0 is again same as 353. Rho 0 T0 is same as 353. So this rho 0 T0 will be get cancelled with this one. Rho 0 T0 cancel with 353. G is cancelled with G, and Tg and rest value will substitute on the right hand side. So what we get is Hg equals to H. Tg will be multiplied inside, m will come in numerator, m plus 1 will come in denominator. So H into m upon m plus 1 into Tg by Ta minus m plus 1 cancel, m cancel, and this Tg will also cancel. So what is left on the second term is minus 1. Same delta P, that is 353 G into H of 1 upon Ta minus m plus 1 upon m into 1 by Tg can also be expressed with the help of the pressure due to the water column, that is rho w into G into Hw. Density of water is 1000. G will be get cancelled. So what we get is 353 into H upon 1000. 1 by Ta minus m plus 1 upon m into 1 by Tg is the meters of water. So that will be equal to 0.353 meters of water, which is equals to 353 mm of water. So Hw is always expressed in terms of mm of water and is given by 353 times H 1 upon temperature of cold air minus air fuel ratio plus 1 upon air fuel ratio multiplied by 1 upon temperature of flue gases. The hot gas velocity in chimney is normally calculated using the equation V equal to under root 2 Gh. So in this case we have Hg minus Hf. Chimney is filled with the hot gases and Hf is the loss due to friction. In ideal case we can neglect the value of Hf. So velocity will be under root of 2g times the column of hot gas equals to Hg. Mass is defined as density multiplied by area multiplied by volume. The area of cross-section area of the chimney is rho g multiplied by A into under root of 2g times the column of hot. The density of the hot gases is given by m plus 1 rho 0 T0 m upon Tg. A will be as it is under root of 2g times Hg. M dot g will be equals to m plus 1 upon m rho 0 T0 upon Tg multiplied by A. We can take out under root 2g common, and instead of Hg we will replace this value by h into m upon m plus 1 Tg by Ta minus 1. So we get under root of h m upon m plus 1 Tg upon Ta minus 1. Now here is a Tg and there is one Tg here, so we'll shift this Tg in the under root sign. Rest m plus 1 upon m is as it is, rho 0 T0 as it is, A will be as it is under root 2g. H will take common because H is independent, Tg will shift inside, so this Tg and this is Tg square in denominator. We will left with m upon m plus 1 1 by Tg into Ta and minus 1 upon Tg square. We will say that this total value equal to certain constant k into under root of m upon m plus 1 1 by 1 Tg minus Ta minus 1 upon Tg square. For to find the maximum discharge, we will differentiate this equation with respect to Tg and equate to. If we differentiate then and equate to 0, we will get a condition for maximum discharge is Tg upon Ta into 2 into m plus 1 upon m. So Tg upon Ta equal to 2m plus 1 upon m becomes the condition for maximum discharge. If you want to find out efficiency, then we have to compare the natural draft with the artificial draft, and in the natural draft we have equation 9.81 into h into m upon m plus 1 Tg minus Ta minus 1, that is the same equation, and how much heat is carried by the hot gases divided by how much heat is carried by the artificial draught is Cpg into Tg minus T2. Efficiency of chimney is always less than 1%.